I want to calculate how much electrical potential energy is stored in some configuration of point charges. In this case, we're going to have 4 identical positive point charges arranged at the vertices of a square. To sort of simplify our calculations a bit. There are a few different ways you can think about doing this. You could, the way I'm going to do it in this example is we're just going to bring in one charge at a time and increment the potential energy that's going to be introduced by bringing in one charge at a time from infinity to its final place. You could also just take the set of charges and add up the potential energy from each unique pair of charges. Or you could take the electrical potential energy for all pairs of charges, and since you'll have duplicates, you take that and divide it by 2. So we make a little table for what we're going to do. Bring in charge and electrical potential energy for that step, and total electrical potential energy. So in our first step, we're going to bring in a charge Q from infinity. And it's just going to sit there. That is the only charge. And bring in charge 1. There is no potential energy for that step because it's not interacting with anything else. And our total electrical potential energy so far is 0. Okay. I bring in a second charge from infinity, so it sits there, a distance d away. So now we have a pair of charges. The electrical potential energy is going to be kq squared over d for that step, and that's how much electrical potential energy we have in total so far. Kq squared over d. Now I want to bring in a third charge to here. It's going to interact with the first charge and also with the second. So bringing in the third charge. Electrical potential energy in that step is kq squared over d for its interaction with the first, and then we have an electrical potential energy for its interaction with the second, and now the distance has changed. Instead of being d away, it's root 2 d away. And I'll add u3 to what our running total is. And so far our electrical potential energy is going to be 2 kq squared over d squared plus kq squared over root 2d. All right, I'm going to bring in our last charge. The fourth charge coming into the last vertex of the square. This is going to interact with the first charge, the second charge, and the third charge. So we'll have 3 pairwise interactions. So for bringing in our fourth charge. U4. So with charge 3 and charge 2, it would be the same term, so I'll just double it. It's 2k q squared over d. And then I have one term for going across the diagonal, plus k q squared over root 2d. And then to get our total potential energy stored, I'll add U4 into what our running total is. So we're going to have 4 terms that are k q squared over d, and 2 terms that are 2k q squared over root 2d. We'll just write out our final answer then. Is this total 4k q squared over d, and I'll clean this up a little bit because I have a 2 over a root 2 plus root 2k q squared over d. And you can check for yourself that the other 2 methods I outlined will give you the same answer. Because basically I would take this charge, have it interact with this one, this one, this one. Those are 3 unique pairs. This one would interact with this one and this one. There's 2 more unique pairs, and this would interact with that one. That'd be the last unique pair. You add all those together in one fell swoop, and you'll get the same total. Or if you don't want to be concerned with unique pairs, then each one of these is going to interact with 3 other charges. So I would have 3 terms, 3 terms, 3 terms, and then 3 terms. So I would take all 12 of those terms, add them together, and then divide by 2. And again, you'll get the same answer.